Hey there, friends. My name's Matthew. I'm the C# artisan, and this is the 9th video in my series on threads. In the first video of the series, I acknowledged that in C#, tasks are really the preferred tool for most parallel processing or asynchronous processing jobs. Tasks are just very easy to use, and they have a lot of advantages. But then I went ahead and said, but hey, let's learn threads anyway, because it's fun, and there are some cases where it's the better choice. So now that you know threads a little deeper, I think it'll be good to do a bit of a comparison of threads versus tasks, so you can really make very educated choices when you're choosing a tool for your parallel programming. And today, I want to focus in on one aspect where the way threads and tasks work is quite different. And this has to do with scheduling the actual work on the operating system, which has implications for load balancing and throughput. The way threads and tasks behave is really interestingly different. So that's what we're going to take a look at. Now, I want to mention that everything we're going to be looking at today is an example of CPU-bound work. I haven't really gone into the distinction between CPU-bound versus I/O-bound work, and it's worth understanding. But at a high level, CPU-bound work is something that, well, is run on the CPU. And if you've got 4 cores and they have a certain speed, that's really what's going to limit how fast you get through the jobs, through the work. I/O-bound tasks are very different. This has to do with where you are waiting for a response from an external resource. And the ones we encounter most commonly are HTTP requests, also database connections, where you've done something and now you're just kind of waiting and twiddling your thumbs and waiting for the result, which may take a while. So tasks are superior for sure for I/O-bound work. And I'm thinking I'll do a video on that as well if I get time. But for today, we're focused just on CPU-bound work. And what happens if I need to do a lot of number crunching on my machine? How is it that tasks and threads behave a little bit differently? So the easiest way for me to demonstrate the difference between tasks and threads here is really just to write some code and show it to you, let you see it live. So I've created a class called threads versus tasks. I've set up a couple of constants here, a count and a duration. And I've got a worker function called SumJob, which we can use for both our threads and our tasks. And all it does is it logs that it started, does some CPU intensive operation for the duration. It'll be a little longer than 4 seconds, maybe 5 or 6, I think. And then it logs that it's done. I've turned off the fancy logger color coding because it gets a little overwhelming in this demo, so it's a little simpler. And now I've got 2 functions for launching this. So again, SumJob is the same. This is the work. We're just initiating the work in 2 different ways. One way we're going to initiate the work is by running it inside of a thread, and the other way will be running it inside of a task. And both of these are set up the same way. We're going to count from 1 to count, or I equals 1 to count, and we're going to either kick off that many threads or kick off that many tasks. So how do we kick off the thread? You should be pretty good at this by now. We can simply create a thread using SumJob in the constructor, and then we can call start, passing in I as the data. That'll do it. We're just going to launch it. We're not going to wait or join on the threads. We're just going to start them. So let's run that and see what it looks like. I've already got the main function wired up, so we can press enter. And one thing I want you to keep an eye on is the CPU over here. So we're going to do 4 threads. They all start right away. Our CPU usage jumps up to about 50%. And then, it was a little long, 9 seconds later, they all stopped. So thread 1, 2, 3, 4 started, and then thread 3, 2, 1, 4 finished. Easy. Now let's do the same thing with the task. And what we're going to use here is we're going to use task.run. which takes a little lambda function, and we can implement that simply by saying some job, just like that. Now, one problem with this code is that we're not going to get the right value of I here. So actually, let's do int copy equals I. Just it moves too fast, right? And this is not thread safe. So we'll copy I, and then we'll pass I, the copy, to some job. So that will kick off 4 tasks, and we're not going to wait all. We're not going to wait for them. We're just going to kick them off and let them run. So now we'll go back to our program and we'll change this to say run many tasks. Let's build it and run it. And once again, I want you to keep an eye on the CPU. We'll press enter. So task 3, 1, 2, 4 started, and CPU went up to about 50%. And they all finished about 9 seconds later. So for a small number of tasks or a small number of threads where the count is pretty close to our core count, this is a 4-core computer, there's no difference at all, except for the fact that the tasks don't necessarily get started in exactly the same order, right? They all get launched, whereas with the thread loop, it did look like we controlled the order a little bit better, but that also could just be an artifact of that this console logs asynchronously. So for small numbers, there's almost no difference. Now let's have some fun. What if we change our count to something bigger, say 12, so 3 times the number of cores that I've got? Let's go back and run the threads. Let's do 12 threads. And to make it run a little faster, I'm going to change this down to 3 and just speed it up slightly. So here we go. I'm going to build it and run it. And here comes 12 threads. They all start. CPU now goes much higher, getting close to 100%. And we're waiting. They're all running. We're going to wait a little bit. I should have had a joke staged here. And then they all finish at the same time. So they all started at 5:31, more or less, and they all finished here right at just about 5:51. And the total time was a little under 20 seconds. So the pattern with threads is they all start and the processor switches between them, right? It's giving a little time to each one of those. None of them are taking priority over the other, and it just kind of like evenly mows through them all until it's done. What happens if we do this with tasks? And now you're going to see the difference. So we're going to now run 12 tasks at the same time. Here we are, ready to start and go. So the first thing you'll notice is that only 8 of our 12 tasks started. That's interesting. And now a 9th one started. That's interesting. And as it's thinking, some of them are starting to finish now, and other ones are starting. And now they're all starting to complete. So the 12th task didn't even start until about 14 seconds in. The whole time from 6:40 to 7 minutes was still 20 seconds. So the total amount of work is unchanged. It's still going to take 20 seconds to get through this work. However, the task framework, it has got some magic to it. It's got some smarts. It is clearly taking a look at how many cores it has available, sort of what the status of the thread pool is and the status of the hardware, and maybe it's even smart enough to kind of understand how much work each one is going to take. I don't really know, but there's some magic going on, and it decided, hey, I'm good to go to start 8 of these. And then as one was probably getting close to finishing, it started a 9th. And then as they start getting completed, it fills in, and it basically optimized your CPU and got you results quicker. So the first results started coming off the the machine, so to speak, faster. So that's really great. Why don't we push it a little more? I'm gonna now take this down. I'm gonna just put this down at maybe 2, and let's push this up to 20. And let's see what happens. And again, if we do this with threads, you can imagine it's going to start all 20, they're all going to run, and then they're all going to finish at about the same time. But what happens with tasks? Let's just keep it with tasks. So if we now run our 20 tasks, so again, it started 8 of them, and it's chugging along using the CPU. And there's the 9th, and now, again, it's starting to switch between them. So it's still thinking. We only have 17 started, and then we finally got through, and I believe they're all, yep, number 20 came in, and it's done. So what you can see is that when you use tasks, you basically get some automatic load balancing happening for you. So this is a great thing, and in many cases, this is exactly what you want. Now, the order that the tasks are started, you've lost control of that. And exactly, when you're going to get the results, they're going to come earlier, but you also don't control when you'll get the results. So if you want to, really orchestrate this yourself, and you want to do the work of saying, hey, I know I've got 16 cores available, and I want to run exactly 16 threads at high priority, and I'm going to schedule things, and you want to do the batching and monitoring and launching and collating the results, great. Right? You can totally do it yourself. It's just a lot of work to get that level of control, whereas the tasks framework is doing something very lovely automatically. Now, right before we finish, I want to show you one other thing really fun, and I'm just going to copy and paste the code in this case. So this is something we haven't talked about at all, parallel for. So you may know that in C# you can do something like parallel.forEach and pass it an action method to do. So what I've done here is I've built a little list of numbers, right? So it's going to, and let me put this back to 12. So it's going to build a list of numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I'm going to call parallel for each on that list of numbers. And each number is going to get sent into some job. So how is this going to run? What do you think you're going to see? So let's just go ahead and wire it up in our program. And let's kick it off and see what it does. All right, we can watch our CPU. So you'll notice that it has started 9 loops. Number 4, number 9, number 1, number 8, number 3, number 5, number 2, number 7, number 6, and then number 10 came in, and then it finished it on out, and now they're all done. So what this has done is it's shown us that the parallel for construct really is built on top of tasks. Okay, so when you use a parallel for like this, it's actually doing something very much like this for you. So that is a very elegant way to do this kind of work. All right, so that's one comparison between threads versus tasks. That tasks just give you a really nice automatic load balancing of work when you're not necessarily sure how much it's going to be and you don't want to spend the time to write all of that load balancing code yourself. It really does a fantastic job for you. Hey there, C# friends. Are you enjoying these videos and finding them helpful? I hope so. And if you are, please go ahead and like the video on YouTube. If you haven't already, please subscribe to my channel and feel free to leave a comment. I would love to hear from you.